For decades, we've been on this massive quest. One of the biggest challenges in science, building a machine that can actually think, that can reason and learn just like we do. But what if we've been looking for the keys in all the wrong places?
What if the secret wasn't about inventing some brand new kind of intelligence from scratch, but about finally decoding the one that evolution has been tweaking and perfecting for millions of years? Okay, let's really get into this. We're going to start by rewinding the clock a bit, about 40 years actually, to this really radical idea from an AI pioneer named Marvin Minsky, a theory that totally flips our whole understanding of what a mind even is. So Minsky argued that your mind isn't one big, brilliant thing. Nope. Instead, he said it's like a massive society, a bustling city of tiny, simple workers, or agents. And each one of these agents only does one super simple, mindless job, like detecting a line or twitching a muscle. Real intelligence, he said, just emerges from their collective chaos. In his own words, trying to find one single, perfect master algorithm for intelligence was a total dead end. The real power, he said, comes from the messy, chaotic, and incredibly diverse way all these simple parts work together. It's a beautiful idea, right? So why don't we have one working on our desks yet?
Well, it turns out that taking that beautiful concept and turning it into working code is monumentally difficult. For decades, researchers have been banging their heads against a few core fundamental problems.
First, there's scalability. I mean, how on earth do you simulate billions of these little agents talking to each other without your computer basically melting? Second, what's called credit assignment. If the whole system does something right, which of the millions of agents that just acted actually deserve the reward? And finally, control. With all these agents just firing off signals, how do you stop the entire thing from spiraling into a useless seizure-like mess? These hurdles have kept the society of mind mostly in the realm of theory, until now.
And this is where it all pivots. This is the big aha moment. What if the solutions to these impossible coding problems aren't actually found in computer science books at all, but in biology?
You see, the key insight here is that the human brain isn't just a vague inspiration for AI, it's a technical manual. It's a working, massively scaled society of mind that has already solved every single one of those hurdles.
I mean, just look at the parallels here. It's like finding the Rosetta Stone. Minsky's theoretical agent is pretty much identical to a biological neuron. They're both simple, they're both reactive, they're both hyper-specialized. Minsky was essentially describing the brain's hardware without fully realizing it. The brain is the blueprint.
So let's get into the really cool part. Let's take those 3 impossible hurdles and see exactly how biology provides a direct, concrete solution for each one.
Okay, first up, scale. Simulating billions of agents that can all talk to each other creates what's called a combinatorial explosion. It's a computational nightmare. So how does the brain do it with 86 billion neurons?
The answer is so elegant. It doesn't connect everything to everything. The brain's wiring is incredibly sparse. Any single neuron is only connected to a tiny, tiny fraction of all the others.
And get this isn't a limitation, it's a feature. Sparse networks are way cheaper to run computationally. They actually learn faster because information is distributed better, and they're way more robust. The brain's solution to massive scale is just to be really selective about who talks to whom.
All right, next up, credit.
When you solve a puzzle, how does your brain know which specific chain of neurons led to that aha moment so it can make that pathway stronger for next time? Minsky's abstract solution was something he called the K-line. He imagined this theoretical wire that would magically form and link up all the agents that were active during a success, basically creating a memory. But, how would you actually build that? Well, biology has this beautifully simple answer. It's a principle you might have even heard of, called Hebbian learning, and it's famously summarized as neurons that fire together, wire together. This is the physical mechanism behind Minsky's K-line. So here's how it actually works. When a bunch of neurons are all active at the same time during some successful outcome, the physical connections between them literally get stronger. That strengthened network is the K-line. It's not a separate wire, it's an emergent property of a really simple local rule. Problem solved. And that brings us to the final hurdle, control. If all your agents are just exciting each other, just shouting, go, 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 you get a positive feedback loop that just leads to pure chaos. How do you tame that system to produce stable, focused thought? The brain's answer, again, is this constant dynamic push and pull. It's not just a society of go signals. It has a whole other population of agents whose only job is to say stop. This is known as the excitation inhibition, or E/I balance. And these inhibitory stop signals are so much more than just a safety brake. They're actually a critical computational tool. They stop that runaway activity, sure, but they also create competition between ideas, which is what allows your mind to focus. They sculpt and refine signals, making thought much more precise. Control isn't forced from the top down. It emerges from this bottom-up balance.
So when you put all these pieces together, you suddenly move from just a collection of interesting biological analogies to a concrete, actionable framework for building an artificial mind.
Let's just bring it all home. The massive challenge of scalability, that gets solved by sparse connectivity. The tricky problem of credit assignment, that's solved by simple, local Hebbian learning. And the absolute need for control, that's handled by an excitatory/inhibitory balance. By translating these core principles from neuropsychology directly into software, we move from a vague theory to a concrete blueprint for building an artificial mind.
Which really leaves us with a final, provocative thought. Maybe this whole decades-long quest to build an artificial mind isn't really about inventing something entirely new. Maybe it's about finally having the tools to translate the masterpiece that's already been built. Thanks for watching.